We are now going to study carefully the matter of matrix multiplication. We'll talk only about multiplication of square matrices, although the best way to do multiplication of matrices of any rectangular shape follows the pattern we'll discuss and makes a good exercise to test your understanding. We'll first apply the theory we developed to give the best matrix multiplication algorithm that uses a single MapReduce job. However, we'll go beyond this theory to explore an algorithm for using a sequence of two MapReduce jobs to multiply matrices. And this algorithm, although more complicated, turns out to be superior to the one-job method whenever communication is the significant cost. I would now like to talk about a very common problem, matrix multiplication, and how we best use MapReduce for this problem. I'm going to cover both upper bounds, the best algorithms, and lower bounds, a proof using the mapping schema idea that the family of algorithms I talk about is essentially the best possible. I'm going to talk only about the problem of multiplying square matrices, but the same ideas apply for rectangular matrices as well, and even to an extent to the extreme case of matrix vector multiplication. I'll refer to the two matrices being multiplied as A and B, and their result as C. We need a way to refer to the element of row I and column J of matrix A, and I'll use A sub I for that. And likewise, I'll use B with row and column subscripts to refer to the element of matrix B in that row and column, and C subscripted the same way for elements of matrix C. Here's the definition of matrix multiplication. CIK is the sum over all j from 1 to n of the product of Aij and Bjk. We actually discussed the relationship between inputs and outputs for matrix multiplication earlier as an example where an output requires lots of inputs. In particular, the inputs for the problem are the two n-squared elements Aij and Bjk, and the outputs are all the CIKs. And CIK depends on all the inputs Aij and Bjk for any j from 1 to n. That is, CIK depends on the two n inputs, those in rows I of A and column K of B. Here's a picture of how you compute CIK. The green point is computed from an entire row of A, that's the blue row, and an entire column of B, the yellow column. There is something special about how inputs relate to outputs for matrix multiplication. We can exploit it in the following way. If one reducer covers both outputs CIK and C, say FG, then we can swap the rows of the two outputs and deduce that this reducer also covers CIG and CFK. The reason is that in order to cover CIK, this reducer must have among its inputs the entire row I of A and then the entire column K of B. Likewise, since it covers CFG, the reducer must have all the row F of A and column G of B. From row I and column G, it has all it needs to compute CIG, and from row F and column K, it has all it needs to compute CFK. We can apply this reasoning to any outputs one reducer covers. If a reducer covers any output in row I of matrix C, and it also covers any output in column K of C, then it has what it needs to compute CIK. As a result, we can find for any reducer a set of rows and a set of columns of C, such that the reducer covers every output that is in the intersection of these rows and columns. Here's a suggestion of what one reducer might cover. It has these 4 rows of A as inputs, and it also has these 7 columns of B as inputs. And as a result, it can cover the 28 outputs indicated by the red dots. In order to get a lower bound on replication rate as a function of reducer size Q, we need an upper bound on the number of outputs that one reducer with Q inputs can cover. First of all, there's no point in providing a reducer with only part of a row or column, so we can assume that to maximize the number of covered outputs, we choose some number of rows of the first input matrix A and some number of columns of the second matrix B. If the total number of matrix elements input to a reducer is Q, then there can be only Q over N input rows or columns. It's an easy calculus application to prove that if the sum of rows and columns is fixed, we maximize the number of covered outputs by choosing an equal number of rows and columns. That is, we cover a square of the output matrix. So how many outputs can we cover? We choose any Q over 2n rows of the first matrix and any Q over 2n columns of the second matrix, and together they yield a square of side Q over 2n, or Q squared over 4n squared outputs. We use the upper bound on outputs to get a lower bound on the replication rate. We need to cover n squared outputs, since that is the number of elements of the result matrix. We just argued on the previous slide that if Q is the number of inputs a reducer is allowed to have, then each reducer covers at most Q squared over 4n outputs. Divide this by this, and you get 4n fourth over Q squared, which is the number of reducers that are necessary. Now, we know that the total number of inputs summed over all the reducers is Q per reducer times this as the number of reducers, or this. That is 4n to the fourth divided by Q. We also know that the total number of inputs is 2n squared for each of the two argument matrices. When we divide this, that again, by 2n squared, which is there, we get the replication rate from here. In the extreme case where Q equals 2n squared, one reducer can take the entire two input matrices and compute the product in the usual serial way. No replication of inputs is necessary, and R equals 1. At the other extreme, we can use a separate reducer for each output. This reducer needs one row and one column. That is, Q equals 2n is the smallest possible Q for which the product can be computed as a single MapReduce job. Thus, every row of the first matrix must be sent to n reducers, one to match it against each of the n columns of the second matrix, and similarly for the columns of the second matrix. Each must be sent to n different reducers. Thus, the replication rate in this case is n. Each of these two examples matches the 2n squared over Q lower bound. There is, in fact, a MapReduce way of performing matrix multiplication using the minimum possible replication for any Q within the range 2n to 2n squared. We do have to assume Q divides 2n squared, however, in order for the bound to be exact. We divide the rows of the first argument matrix into G groups of n over G rows each, and we do the same with the columns of the second matrix. Then for each pair of groups, one from each matrix, we have a reducer that produces all the outputs that can be computed from these groups. That is, there are G squared pairs of groups, and Q is the number of elements in n over G rows and n over G columns. That is 2n squared over G. The replication rate is G, since each element must be sent to G reducers, one for each group that needs to be matched against the group of rows or columns. We solve for G in terms of Q. And we get R equals 2n squared over Q. Here's a picture of what one reducer does. It gets a group of rows, the blue, and a group of columns, the yellow. With these rows and columns, it is capable of computing a little square of the output matrix shown in green. To compute the entire output, you need G squared reducers, each one covering one of the little squares of the output and needing an entire group of rows and a group of columns as input. I now want to talk about a different approach to doing matrix multiplication by MapReduce. It turns out to be at least as good as the algorithm we just discussed as far as communication cost is concerned. But it uses not one MapReduce job, but two. That is, What we discussed so far, where we divide rows and columns into groups, is the best one-job way to multiply matrices. But if we use two MapReduce jobs in sequence, we can do better. For the first MapReduce job, we divide both input matrices into small rectangles. A reducer gets the elements in two of these rectangles, one from each input matrix. No reducer can produce any output completely, but it contributes to a square of outputs. The second job simply sums the contributions to each output from the various reducers of the first job, thereby producing the correct output elements. Here's what we see a typical reducer of the first job does. It gets an input that is a rectangle of the first matrix. This rectangle is twice as high as it is wide. That turns out to be the way to minimize the total communication used by the two jobs together. We won't prove this, but it is indeed the case. Let cap I be the set of row indices defining the blue rectangle, and cap J the set of column indices. Now look at the yellow rectangle in the second matrix B. We only need a reducer for this pair of rectangles if the rows of the yellow rectangle, J, have the same indices as the column indices of the blue rectangle. And we've called the set of indices J. The rectangles of the second matrix are twice as wide as they are high. We'll use K as the indices of the set of columns for the yellow rectangle. And when we multiply the blue and yellow rectangles, we contribute to the outputs in the green square of the result matrix C. The green square has cap I as its set of row indices and cap K as its set of column indices. That is, what you get for the element in row I and column K of the result matrix C is the sum over all little j in the set of common indices of the two rectangles, that is the set cap J of the product of Aij and Bjk. That's not enough to get the entire sum for the output element Cik, but if we divide the columns of the first matrix and the rows of the second matrix into groups, let's say like this, then there will be a lot of blue rectangles with the same set of rows I, sort of these. And there'll be a lot of corresponding yellow rectangles. Each blue rectangle pairs with the corresponding yellow rectangle, like this, that. And they each contribute to the same green rectangle. So all the second MapReduce job does then is to sum the corresponding contributions to the output Cik from the different set of indices cap J. Now I want to describe the first job in more detail. Begin by picking a number G, the groups. We'll divide both rows and columns into groups, but the groups will have slightly different sizes. I'm going to assume that 2G divides N. We'll divide the first matrix A into rectangles that are n over g rows by n over 2g columns, like the blue rectangle on the previous slide. That is, the rows of A are divided into g groups and the columns into 2g groups. We'll do something similar but slightly different for the second matrix B. Here the rectangles consist of n over 2g rows and n over g columns of B, like the yellow rectangle on the previous slide. That is, B's rows are divided into 2G groups, and its columns are divided into G groups. We don't have to constrain which rows or columns go into which groups, with one exception. The groups of columns of A must each have a set of indices that is the same set as the set of indices for some group of rows of B. That condition will be satisfied if we do the obvious partitioning into groups, put the first n over 2g columns of A into the first group, the next n over 2g columns into the second group, and so on. Then do the same thing with the rows of B. I'll also assume we do the obvious partition for the rows of A and the columns of B, but there we do not. We use groups of size n over g rather than size n over 2g. We want a reducer for each pair of rectangles, one from A and one from B, as long as they share the same set of indices cap j for the columns of A and the rows of B. We need a name for the reducer, and I'll use ijk. You can think of I as either the set of rows of A involved in the first rectangle or as the name for that group of rows. And similarly, k is the set of columns of B involved in the second rectangle. And j is both the set of indices for the columns of the first rectangle and the set of rows for the second rectangle. Again, remember that the only time we have to multiply two rectangles is when they share the set of indices cap j. Other pairs of rectangles have no intersection between the columns of the first rows and the rows of the second, and therefore their elements are never multiplied together to get any output element. Here's the picture of the two rectangles multiplying to contribute to a square of the output elements. The dimension of each rectangle in terms of the parameter g is shown. It is important to remember that when we multiply the blue and yellow rectangles, we don't get the complete matrix product in the green area. We get a contribution to those output elements. And there are 2g different values of the set of indices cap j that can be paired with the same set I and the same set k. Each of these triples correspond to one reducer, and each of these reducers contributes to the output elements in the same green area. The function of the second MapReduce job, as we have said, is to sum these contributions to get the correct value for each output element. Now I want to lay out what the mappers and reducers actually do in the first job. Before I do, I want to use a convention. Lowercase I, j, and k will represent individual row and column indices. Little I is a row of the first matrix A. Little j is both a column of A and a row of the second matrix B. And little k is a column of B. Then I want to use the corresponding capital letters to represent the groups into which these rows or columns fall. That is, group of rows capital I is always the group of A's rows to which the row little I belongs, and so on. The mappers will handle elements of both matrices A and B. Let's see what it does when given an element Aij. First, it will generate G key value pairs. The keys will be capital I, J, K for any group capital K. But capital I and J are the particular groups into which row little I and column little j belong. The value will have enough information for the reducer to figure out what is going on. It needs to know A, that is, that this is an element of input matrix A rather than B. It needs to know I and j, and so it knows where this element fits into the matrix A, and it needs to know the value Aij. For elements of B, the mapper does something very similar. It also generates G key value pairs, but now groups J and K are fixed, and only group I can vary over the G possible values for that group. And the value tells the reducer this is an element of B. It's located at position I and j, and that its value is bjk. The reducer for key ijk takes all the elements it has received and sorts them by the row little I of A and the column little k of B. That row-column pair gives us the output element to which the contribution is to be made. It then sums over all little j, the product of Aij times bjk. We'll call the result x sub ijk. Notice that I and k are row and column, respectively, while capital J is a group. And job 2 is really simple. The mappers take each xijk and turn it into one key value pair. The key is ik, and that is the index of the output element that xijk contributes to, and the value is xijk itself. And what do the reducers do? The reducer for I and k simply sums all the associated values. These are the contributions to the output element Cik. I want to talk about whether using one MapReduce job or two is likely to give better performance for matrix multiplication. The answer is a little bit of a surprise, at least it was to me. First of all, let's talk about computation time. We'll look at communication cost after that. I claim that the same arithmetic is done by either method. You need to multiply each aij with each bjk, and both methods do each of these multiplications exactly once. And you need to sum the n terms that give you each output element. Both methods do these sums once, although they group the terms in different orders. Now, there's a general bias against using more than one MapReduce job if one will do, because setting up a job requires some overhead. And also, one often has to wait for the last task associated with a job to finish, so having two jobs forces us to wait twice rather than once. However, as we shall see, the difference in communication cost can be so great that it strongly indicates for the two-job method. So I want to do the comparison of the communication cost using one or two MapReduce jobs. We already know what it is for one job as a function of the reducer size q. We deduced that the replication rate was 2n squared over q, and there are 2n squared inputs, so the total communication is the product of the replication rate and the number of inputs, or 4n to the fourth power divided by q. We need to analyze the two-job method. We'll do it in terms of the parameter g, the number of groups of rows of the first matrix. Later we'll relate g and q so we can get a comparable function for communication in terms of n, the matrix size, and q, the reducer size. Job 2 is easier to analyze. First, we'll assume that the mappers for the second job execute where the data is, so there is no communication of data between jobs. The communication cost of the second job is 2n squared times g. It is the product of three factors. N squared over g squared is the number of squares into which the result matrix is partitioned when g is the number of groups. And each square has g squared elements. And two g reducers contribute to each square. That explains where the 2n squared g comes from. Now let's figure the communication cost of job 1. There are 2n squared input elements, and recall that each input is sent to g different reducers, where g is the number of groups. That means job 1 uses 2n squared g communication, exactly the same as the second job. Incidentally, that was no accident. We picked the 2-to-1 aspect ratio of the rectangles exactly so the two jobs would require the same communication, and this total communication is a minimum. If we had done the more natural thing of dividing input matrices into squares, we would require about 6% more total communication. So the total communication of the two jobs is 4n squared times g. Now we need to relate g and q so we can get rid of g and express the communication in terms of n and q only. In the first job, each reducer gets two rectangles. Each is n over g by n over 2g, which explains this term. And the factor 2 is there because there are two rectangles input to every reducer. So q is n squared over g squared. Or reversing the relationship, g is n over the square root of q. When we replace g in the total communication, we get 4n cubed over the square root of q. Remember that for the single job method, the communication is 4n to the fourth over q. If q equals n squared, those are the same. But for q smaller than n squared, the two-job approach wins out. For example, if q is 2n, the minimum possible for the one-job method, then the one-job method takes communication 2n cubed, while using two jobs keeps the communication to 2 square roots of 2 n to the 5 halves.